Welcome to this explainer. Today we're diving straight into the fascinating mechanically synchronized world of the traditional automotive ignition distributor. If you've ever popped the hood of a classic car and stared at that crazy, multi-wired spinning contraption wondering what on earth it's actually doing, well, you're in the right place. We're going to break down exactly how this mechanical brain orchestrates the heartbeat of an internal combustion engine. Here's our roadmap for today. We'll quickly cover 1. The setup. 2. Anatomy of a distributor. 3. Creating the high voltage. 4. Timing the perfect spark. 5. The complete ignition journey. And finally, 6. The shift to modern ignition.
Okay, section 1, the setup, the mechanical traffic controller.
So here's the core challenge. A multi-cylinder engine absolutely needs multiple sparks to ignite the air-fuel mixture in each and every cylinder. But traditionally, an engine only uses one ignition coil to generate all that power. So you've got this massive logistical puzzle, right? You need a device to route that single powerful spark perfectly to the correct cylinder at the exact right millisecond. And that is exactly where our distributor steps in. A great way to picture this is to think of a railway system. The ignition coil, that acts as the power generator, creating the electricity. The distributor is your central switching station, and the spark plug wires are the different tracks leading out to each cylinder. Just like a switching station directs a single train down various tracks to reach its final destination, the distributor takes that power from the coil and seamlessly switches it to the correct spark plug wire.
Now, let's clear up a huge misconception right off the bat. Here's the golden rule. The distributor does not create the high voltage itself. Not at all. The ignition coil is the real workhorse here. It creates that high voltage pulse, which can literally reach tens of thousands of volts. The distributor merely acts as the router. It's just channeling that incredible energy without generating a single volt on its own.
Moving on to section 2, anatomy of a distributor. Inside the cap.
Pop the cap off, and inside we find this beautifully choreographed mechanical dance. Step 1, the distributor shaft is physically synced to the engine's camshaft, meaning it rotates at exactly half the speed of the crankshaft. Step 2, mounted right on the shaft is the central rotor spinning constantly. It pulls in that high voltage from the coil right through the center of the cap. And then step 3, this is where the real magic happens. The rotor acts as an electrical selector. But get this, it doesn't actually touch the outer terminals connected to the spark plugs. Nope. As it sweeps past them, it forces that massive voltage to jump a tiny air gap. It is literally creating a controlled lightning strike inside the cap hundreds of times a minute. Which brings us to section 3, creating the high voltage. The trigger. So how does the system know exactly when to unleash that massive voltage pulse? This is where the mechanical genius really shines. In these older systems, the distributor shaft has a mechanical cam on it. As the shaft spins, this cam physically pushes a set of electrical switches called contact breaker points, open and closed. When the points close, a standard 12-volt current flows from the battery into the ignition coil, letting the coil charge up a magnetic field. Then, right at the exact moment a spark is needed, the cam forces those points open. This sudden, violent interruption of the primary current causes the magnetic field inside the coil to just instantly collapse. And that rapid collapse? That is exactly what induces the massive high-voltage spark in the coil's secondary winding.
But wait, there's a huge catch here. When those breaker points suddenly pop open, the electricity doesn't just want to stop. Because the coil is an inductive load, the current desperately wants to keep flowing. Left unchecked, it would just jump the gap between the opening points, creating a destructive electrical arc that would literally melt and destroy those mechanical contacts in a matter of minutes. So, how on earth do we solve this?
Enter the unsung hero of the traditional distributor, the condenser. It's a small component connected right across those breaker points. In that split second when the points open and the electricity tries to jump the gap, the condenser temporarily acts like a sponge. It absorbs that residual electrical energy. This completely suppresses the arc, allowing the points to open cleanly. Thanks to the condenser, the coil can generate a strong, clean, high-voltage pulse without completely frying the delicate internals of the distributor.
All right, section 4, timing the perfect spark, dynamic adjustments.
Now, engine conditions are constantly changing, right? So the distributor automatically adjusts its timing on the fly, purely using mechanical physics, in 2 brilliant ways. First, you have centrifugal mechanical advance. Inside the distributor are small weights and springs. When you stomp on the gas and the engine spins faster, centrifugal force naturally flings these weights outward.
This movement physically shifts the internal mechanism to trigger the spark slightly earlier, perfectly matching the higher engine speed. Second, there's vacuum advance. This uses a little diaphragm connected to the engine's intake manifold. When you're just cruising along under a light load, intake vacuum is high, which pulls the diaphragm and advances the timing to maximize your fuel efficiency. It is literally an elegant, purely mechanical computer.
Let's pull it all together in Section 5, the complete ignition journey, firing order. The distributor has to strictly follow the engine's specific design, which in a lot of four-cylinder engines is a 1-3-4-2 firing order. The distributor rotor continuously spins past the cap terminals, nailing this exact sequence at lightning speed. It takes the coil's voltage, jumps the gap to terminal 1, then 3, then 4, and then 2. This cycle just repeats continuously, thousands of times a minute, seamlessly translating electrical pulses into perfectly synchronized mechanical combustion. If these wires ever get crossed, the spark arrives at the wrong cylinder at the wrong time, and the engine will just instantly misfire or flat out fail to start.
Section 6. Shift to modern ignition. Why did distributors disappear? As brilliant as this system is, the distributor has one fatal flaw. It relies entirely on constantly moving physical parts and massive high-voltage arcs. Because of this, it is incredibly susceptible to mechanical wear. Those contact points, they physically burn away, shifting your timing and totally killing performance. Distributor caps get cracked or develop carbon tracks, causing tens of thousands of volts to leak to the wrong places, which gives you terrible engine misfires. Even the bearings on the shaft eventually wear out, giving you wobbly, erratic timing. It was just a system that required constant, exhausting tuning and maintenance just to keep the engine running smoothly. To ditch all those mechanical failures, the automotive industry shifted gears entirely. Modern engines replace the mechanical distributor with a super robust array of electronic components. Today, we rely on an electronic control unit, or ECU, acting as the brain. Instead of a spinning shaft, you have hyper-precise crankshaft and camshaft position sensors telling the ECU exactly where the engine is in its cycle. And perhaps most importantly, we use individual ignition coils, known as coil-on-plug systems, placing a mini ignition coil directly on top of each and every spark plug. So, looking at the whole evolution, we totally traded that single coil and complex spinning mechanical router, a thing just filled with wearing points, spinning weights, and jumping sparks, for the modern solution. And that is multiple individual coils, governed entirely by computer logic and solid-state sensors. There are zero moving parts to wear out, no high voltage jumping across air gaps in a plastic cap, and timing can be adjusted by the computer thousands of times a second with absolute perfect precision. But it does leave you wondering, doesn't it? While modern electronic ignition is undoubtedly more reliable, more powerful, and virtually maintenance-free, isn't there something truly magical about the classic distributor? Knowing how flawlessly it choreographed tens of thousands of volts using nothing but spinning weights, physical vacuums, and controlled lightning across tiny air gaps, have we lost a piece of kinetic art in our pursuit of electronic perfection? Thank you so much for joining me on this explainer, and definitely keep that question in mind the next time you turn the key.